Well, now see there is two possibility here that this OH will attack on this carbon, planar carbon sp2 hybridized from this side or from the back side. So there are two orientations of OH group, right? I'm keeping this O on the same plane, but OH, I'm changing the OH orientation, right? So see how to plot the structure. I'm taking this on the same I mean plane and changing the orientation of OH. This is C, this is C, this is O, and this OH, this side, H, this side. So OH and H. Now rest part is same. Put OH here. This OH is here. This OH is here. And CH2OH, right? And now see how many stereogenic carbon now. See, this is stereogenic, this is stereogenic, this is stereogenic, and this is stereogenic. So these are four stereogenic carbon are there in the cyclic structure of glucose, right? Sorry, in the open chain. But here in the cyclic structure, see if you examine this carbon is also stereogenic. Means now there are five stereogenic carbon. So n is equal to 5. N is equal to 5. Okay. So now the stereogenic carbon in the cyclic structure of glucose are 5. So if you see here, this is carbon number 1, this is carbon number 1, this is carbon number 2, this is carbon number 3, this is carbon number 4, this is carbon number 5, this is carbon number 6. So with respect to carbon number 1, we have two isomers in which the configuration is this OH this side and here OH on this side. You know, this isomer related to the carbon number 1, this is called anomers, right? So anomers, right? So what are anomers? Anomers are the isomers related to carbon number 1 in aldohexoses and and carbon number 2 in ketohexoses, right? Now the naming of this is very crucial and very important. So please listen carefully. See this carbon number 1, how to name this isomer. So there is a rule, and I mean, at many places you will find different explanation, but what I am explaining here, this is the perfect and as per the IUPAC system. See, carbon number 1 and carbon number 5, you have to see these groups. CH2OH you have to see, and OH. OH. If they are opposite in the Haworth formula, this formula is known as Haworth formula. Haworth formula. 6-membered planar ring, and it is mandatory that oxygen should be the top of the right hand side. Top of the right hand side means this oxygen you cannot take here or here or here. This is I mean convention. This is not any rule, but this is a convention, right? So this Haworth formula with this structure, if your oxygen here in the top right hand side, so if C5 and C1, if configuration means bulkier groups of C1 and C5, if they are opposite, then this anomer is known as alpha anomer. Alpha anomer. And if the bulkier substituent of carbon number 1 and carbon number 5, they are in the same plane, same side, then this is called beta anomer. Beta anomer, right? So alpha anomer and beta anomer, this is the best way to determine. Suppose that examiner will give you some this structure not like this. The oxygen is here or somewhere here. So you don't see anything whether oxygen is here or not. This is the proper Haworth formula for sugar. But if it is not, examiner try to check whether your concept is clear or not in case for anomers. And if they have given this oxygen here and they have inverted, so don't see anything to decide alpha and beta. Just see, find the carbon number 1 in aldohexoses and carbon number 5 in the ketohexoses. Carbon number 2 in ketohexoses and carbon number 5. In both the cases, carbon number 5 is same. So I will let you know by taking one example of ketohexose. So this carbon number 5 and carbon number 1, if bulkier groups have opposite, right, then this is alpha. And if on the same, then it is beta, irrespective of in what form they have given this. Clear to everybody? Okay, good. And so alpha anomer, C1 and C5 bulkier substituents are opposite, right? And they are in the same site. Hopefully it is clear. So this alpha and beta, this structure, this and this one, this is 1, this is 2. So 1 and 2, they are anomers. 1 and 2 are anomers. And you know, this is the reason why if we take a freshly prepared solution of glucose, it shows two different optical rotation. This is due to these anomers, alpha and beta, right? Means the pure glucose, what you are getting from the market, what you are taking, that D-glucose, that is not the pure substance. That is a mixture of this alpha and beta. And I think this beta contributes 63%, I think, and 63, approximate 63% is this, and 36% is this, 37% is this, and a little bit open chain structure, right? So alpha and beta, in which beta anomer is more stable than alpha because its population is more uh, at equilibrium, right? So now, how to name this compound? You can name. You have to every time you have to put this alpha or beta, and you have to see this orientation, this bond orientation, right? This and this, right? This is important. So OH, so this OH and CH2H are opposite, so you have to write alpha, and this is D glucose, so D and glucopyranose, right? OSE suffix, OSE suffix we have to use when this anomeric OH is free. All these are very important points. O's when anomeric OH is free. Anomeric OH is free, right? And this is called beta D glucopyranose, right? Okay. See this alpha D glucopyranose, alpha D glucopyranose. This is in equilibrium with open chain, and this is in equilibrium with beta D. This is approximately 63%, this is 37%, and this is 0.01%, right? And this is the cause of this mutarotation. This is the cause of mutarotation, that this alpha D will convert into beta D, beta D convert into alpha D. So the optical rotation of this is 18 degree, and of this is 112 degree, right? And this will 54 degree. So with time, this converted into angle of rotation decreases, and for this alpha D it is increases, and of this it is decreases. So this is the cause of mutarotation. Cause of mutarotation, that they will alpha and beta, they will convert into each other, right? Now see, suppose that in glucose structure you have given this type of arrangement. OH is given like this, means the alpha or beta not specified, not specified, right? So if alpha or beta is not specified, then this zigzag line is shown like this. OH, OH, OH. So this is also a convention, that if this type of arrangement is given, then this is suppose that if this type of arrangement is given, then it is clear that it is below the plane. If this type of symbol is given, then above the plane, and if this type of symbol is given, then it is not certain that it is above or below. right? Above or below. So this is the representation of what uh, I mean cyclic structure of glucose. So hopefully all of you are clear. So cause of mutarotation is the uh, interconversion of this alpha and beta into each other. Okay. So this is the structure of what cyclic structure of glucose. Okay, good. Now see, if you want to draw the structure of mannose, then all of you are knowing that mannose is the 2 epimer of glucose. So since it is 2 epimer of glucose, so now see OH, H, CH2OH, OH, OH, and OH. This is the alpha. See this OH and CH2H alpha D glucose. But this is mannose is 2 epimer of glucose. So what you have to do, change the orientation of this OH, right? Like this. So now this is alpha D uh, mano pyranose. Pyranose. Alpha D mano pyranose. Similarly, you can draw the beta D pyranose. This is homework, right? All of you should draw this. Okay. So this is cyclic structure of glucose, mannose. Similarly, if you want, you can draw. That is also homework for you people. Draw the structure of. This is another homework. Draw the structures. Draw the structures of alpha and beta D galactopyranose. So draw both the structures. Okay. Now see ketohexoses. So we have one example of keto sugar, that is what fructose. So CH2OH CO CH2OH, OH, right? So this is D fructose, D fructose, keto sugar. What is the numbering of this? See, 1, 2, 3, 4, 5, 6, right? So do this is the anomeric carbon here, carbon number 2. This is anomeric, anomeric carbon, right? Do the same thing as in the case of glucose. Now the interglycosidic linkage will form between 2 and 5, right? 2 and 5, this. So C2 and C5, C5, right? They will combine with each other and produces the 5-membered ring, produces the 5-membered ring, right? So do the same thing, rotate this like in the clockwise and make the folds at the different carbon, so you will get this type of, this is CH2OH, carbon number 1. This is CO 1 2 3. So if we are doing like this, so OH will go up, and 4 and 5, these two OH are coming down, right? And H, CH2OH. So see, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. So 5 OH is here. So you have to bring this OH over here. So first you have to exchange this H with CH2OH. This first exchange H with CH2OH, and then H with OH. So after 2 exchange, configuration of this carbon number 5 will be remain same. So 2 exchange of groups, exchange of groups, right? So if we do the 2 exchanges here, so hydrogen will come here, CH2OH will come here, and OH will come here. Now this OH will attack here. So similarly, now this bulkier group is here, CH2OH. So CH2OH have 2 orientations, and we get 5-membered ring. This is 5-membered ring, furan ring. So now the CH2OH and H, right? Sorry, CH2OH and OH. This is up, this is down, this is right? Now see, this is carbon number 1, this is carbon number 2, this is carbon number 3, this is carbon number 4, this is carbon number 5. So again, this is the I'm in more prior group. If you do the priority, this will get the first priority. So this and this. So you have to see, don't see priority or any other thing. OH of anomeric carbon and fifth carbon CH2OH. They are opposite, means this is alpha D fructo furanose. This is furan ring, so this is furanose. O's why? Because this two carbon OH is free. Second carbon OH is free. Okay. So this is alpha D fructofuranose. Similarly, we can draw the beta D fructofuranose. The only possibility is this, that one more possibility here is OH and CH2OH. So this OH and CH2OH, fifth carbon and second carbon both are in the same plane. So this is beta D fructofuranose structure. And these two are anomers. These two are anomers. So whenever alpha and beta suffix prefix is coming with this carbohydrate, immediately you should understood, okay, this is they are anomers, right? So this is the cyclic structure of glucose and fructose, mannose and galactose you can draw, right? So in the next lecture, I will discuss this reducing and non-reducing sugar, how to identify, and then structure of disaccharides, maltose, galactose, and one more reaction, epimerization, and after that some structures basically. So most likely in the next lecture we will complete this.